Okay, 7 o'clock. Let's get started. All right, today it's on the review of lecture 4. Lecture 4 is talking about recursions and iteration, two ways of making looping. As you can, by now, you know that these are the power of computer with small programs with using recursion and iteration. You can actually solve amazing problem like making all the beautiful pictures. And so the lecture 1 and lecture 2, we talk about either to use of either and throw you into playing with Python. Then lecture 3, I did a review on problem solving, and that those are some strategy or some thinking that you should have when you're trying to solve problems. Now, once you know how to solve problem with recursion or iteration, the next question is naturally, how good is my solution? Okay. So today we want to talk about that. And how good is your solutions? It's actually got to do with the order of growth. We are not interested in the absolute time that you take a stopwatch and try to time your algorithm, but rather we are interested in how your program behave as the size of the input changes. Okay, so for that we have functions, as you will see in your recitation number 2, that we will go through the details about that, and we use functions to characterize things so that it's fair and it's scalable and so on. All right, so the first keyword that you know, I put it here, it's simplicity. That is to say that we look for solutions, but usually we look for simple solutions. As I encountered that yesterday when I saw the solutions from many of you, then it can be a simple problem, can have many ways, but some of the ways are actually too verbose, too much. What we strive for, usually it's a simple solution. Okay, of course, this takes some practice. For example, in the case of leap year, you can list out all the cases. And of course, you can also use some simple combining some of these cases into some simpler, easier to understand solutions. Okay, so I hope that you are looking forward to making solutions simpler. All right. But before you can make things simpler, of course, the first thing you have to do is to make sure your solution is correct. All right. If it is not correct, there's nothing to talk about. All right. So correctness is the first thing that we strive for. Now, what is the correctness? Correctness, it actually means that you are meeting the objective. I talked about that last week. How do you work on your problem? You work on your problem by identifying the objective of the problem. And from the objective, you may be able to break it down into smaller objectives. And then you tackle each of these smaller solutions. And then you combine them in a bottom-up or top-down manner to get your answers. But one thing that I may have not emphasized much is that actually objective, it comes with assumption. All right, so you could have assumed that your input it's never wrong. In that case, you do not need to do error checking. Like in the case of our recitation number 1, we had the combo. We can assume that a combo number given to you 1 to 8, it's always correct. Nothing beyond 8 and nothing below 1, and nothing about fractional number and so on. All right, so objective usually come with the assumption. We write programs to meet the objective. At the same time, we took some assumptions. Our assumptions are such that we do not have to write extra codes in a way. But this particular paragraph here, it's to make things even clearer to you. So when a program is correct, it is because it is meeting the objective that comes with assumption. So not long ago, actually, long time ago, maybe 25 years now, people took, or maybe a long time ago here, refers to that computers started in the 60s and 70s. When we had the computer systems, we actually keep the year in 2 digits. For example, a person who was born in 1960, it's been kept as 60, all right, instead of 1960, and so on. All right, so anyone born in 1999 is recorded as 99 only, ignoring the first 2 digits, which is 19. All right, in doing so, you actually save some storage. Because at that time, storage is actually not cheap, unlike today. Uh, uh, but because of that, the numbers are kept as 60. So instead of a full 1960, nowadays we are now in 2026. If you take 26 minus 60, you are in trouble because 26 minus 60 doesn't give you the age of the person anymore. All right, so all these calculations by doing this simple formula, which was correct by the assumption that all years are in 19th century or 20th centuries. All right, but now you cannot do that anymore. So they pay the price by having to upgrade their systems. This is called the millennium bug, and a lot of effort was put in there, especially in the banking system, where a lot of the system was built with only 2 digits. This was coined as Y2K problem. All right, but do remember, whenever we say we are correct, we are actually meaning that we are meeting the objective with certain assumption. All right, so here is just another point to uh, shout out that you have to do testing always. It's needed to secure good correctness that each statement in your code must have been exercised during testing. We will come to that in lecture 5 also. Next week's the review. I will show you some of the tricks here. So not to forget testing, it's an equal part, it's an important part, as I mentioned before. You write code very quickly, but you spend pretty much 10, 20 times the time to actually test your codes. Okay, so writing is easy, but testing, it's the one that you're spending most of the time. Okay, so once you have strike to be correct, then you can talk about good or not. All right. So we talk about good or not in two things, time and space. All right. Time is money. If you take a long time to compute it, you are waiting and waiting. That costs you time. Space here means that the space that people keep is the hard disk, the storage. All right. That space. So we always judge a solution based on their time and the space. And nowadays, space is less important because space is much cheaper, whereas time is still money. Okay, so we do take care of the time and space, all right, with time more important than space in general. Okay, one remark first before we talk about time and space. In actual fact, other than time and space, there's other ways to judge whether your solution is good or not. All right, this is in line with in computer, we do not, I must strike that, I must emphasize that we are not always trying to automate things. We are always wanting to innovate. Okay, so automation is enabled by the computer system, but automation itself is not what we look forward to only. We wanted to innovations to means that we can use automation to change the way that we work. It's depicted. This is more if you use ThinkPast. Okay, your generation may be using ThinkPast more than our generation. Using ThinkPass, it's really a new way of authenticating yourself to the computer system to gain access to all the sensitive information and so on. All right, and this is really an innovation because it doesn't just simply automate the process, but it also change the whole process of doing things. This is actually in the study of UI UX, means user interface and user experience. All right, our course here is not about this, but you will encounter this in the when you study computer science in a higher level. This is equally important part of time and space. Time and space is absolute. It's talking about the how fast you can get things. But when we use UI UX, we are actually interested in the experience that the user of your system is going through. So this is equally important, but these are more social behavior kind of stuff that it's not the technical thing that we are talking about in this course. So, but I want you to take note that these are such a thing, they are around. Okay. All right. Now, the next thing that, so what we do is time and space. The scientific way of doing things of what is good or not, it's talking about the resources. So resources here refers to the time and space. But one thing that you should uh, remember, it's that it's possible, all right, in various occasions, if you are willing to pay for a space, you can actually get faster time. Okay, for example, all right, in the extreme, if you have unlimited amount of space in the world, then if you keep all your solutions in the storage that you have, then the time that to get the answer is simply constant because you just simply look it up and you get an answer. All right. But of course, this is impossible, right? Because you cannot have the space big enough to keep all your solutions. Okay. So that is, even though that is the case, but we do have a trade-off of the time and the space that you will experience as you move around when you study more in our course. So in the first part of our course, we talk about how to solve problem with actually dealing with the time. In the second part of the course, we talk about how to use data structure, which is involved the space. All right. With the correct data structure, actually you can at times solve the problem much quicker. Okay. So not to forget this statement that I say here. But one thing to note is also that time itself, once you spend, it's spent. It's the money when you spend it, it's gone. But space, when you spend it, they're actually the footprint, as you will see in the recitation number 2, that the space can still be there. You can overwrite it, you can reuse it basically, and you don't pay extra. You just have to pay whatever the maximum amount that you use at any one point in time. All right. So this first point says that space tend to be a major or equal weightage issue, but not so much nowadays because hardware or memory is quite cheap. But we cannot assume we have unlimited amount of space still. Okay. On the other hand, the flip side is that Apple Watch, for example, or any of these embedded systems, small systems, they still need to take care of the storage space because the lesser storage you use, the program that you need to run on these devices, you can then run it. Okay. And they want to make device as elegant as possible and as small as delighted to the consumer. Right, so space is still also in some sense still there. And about time, right? So this is the main issue, or I would say, in compared to the space. But we do not do the absolute clock to get the time. We actually do growth rate. All right, as you will see. What we mean is that we want to judge a program based on how the program behaves when the size of the problem increases. Okay, so if you give me 10 numbers, how do I behave? Then when you give me 100, which is one order of magnitude higher, how do I behave? Then you give me 1,000, which is another order of magnitude higher. How do I behave? So that is the growth rate. The growth rate is more important than the absolute time. As you know, your computer and my computer are quite different. The time that you get the time that I get running on the same input are not going to be the same because it could be a faster computer than my computer, which is 3, 4 years old. All right. So absolute time is not the correct measure, but the growth rate is what we look for. All right, when we judge. And the growth rate, as you will see shortly in the next segment when we do our recitation. All right, our recitation, you see this growth rate and so on. This is the way that we're going to judge how good our program is, and we will talk about this after 8 o'clock. Okay, so in computer science, there's a few terms that I need to tell you, all right, so that you bear in mind. So when you read literatures or you browse net, you know them. Okay, first thing is that computer usually when computer science itself has theory, there's theoretical study of computer science, what is possible, what is not possible. Okay, so what is possible usually means you can tell yes or no at the same time. Not what is not possible means that I can sometimes I cannot tell. Only some specialized case I can tell. And in that case, it's always using zeros and ones to tell you. So a problem is decidable if you can always tell yes or no. And a problem is undecidable if you cannot tell yes or no all the time. Okay, such a thing happen. It's there. It's called a halting problem. This is a problem that will take input someone else's program to check whether this program will ever stop or not, or will ever end or complete the execution or not. All right. So this is a halting problem. This halting problem is not decidable. Okay, it's undecidable. All right, I'm just giving you an example to tell you that, hey, don't try to solve all the problems in the world. Okay, because there are problems in the world that we cannot solve. Okay, and as a trained computer science person, you should take that to your heart in the sense that don't blur to or try to I can always write a program for it. No, that's not the case. Okay, there are computational problem that you cannot write any program to solve it. Okay, and not you, not me, and not anyone else in the world. Okay, the next word is that if a problem can be solved, all right, a problem, so we don't care about this kind of problem. This kind of problem in some sense, they are theoretical. Okay, once you know it, okay, don't try to touch it for now. If there are problems which are here decidable, they're still decidable also will take different amount of time. Right? You can have a different amount of time, like this kind, 2 to the n. This is ridiculous, right? If you have a size of 10, you're going to use 1024 step. If you have size of 100, 2 to the 100, wow, that number is ridiculous, okay? So this is not what we call not tractable anymore. It's called intractable, right? So the two words are tractable means that the problem can be solved in polynomial time. Why polynomial is important? Because polynomial is n to the power of something, n to the power of 5, n to the power of 2, n to the power of 3, those kind of things. These are things which are human, which you encounter often, and they are pretty good in solving problems. On the other hand, if intractable means that it cannot be solved in polynomial time. So these are problems that are meaning that they are undecidable also in a way that they use exponential amount of time. Okay, so like what you saw just now, the slide, the power, this, all right, this is to the power n. This is the Tower of Hanoi, which is the one of the question here. All right, this question, Tower of Hanoi, that you're going to take to the power n times to solve it. And this is not tractable. Okay. All right, so the two words from decidable, undecidable to tractable, intractable. All right, even tractable polynomial, I did mention just now that the number could be n to the power of 5. N to the power of 5 actually is pretty bad. All right, what we usually solve is n to the power of 2 in general. Okay, n to the power of 2 or below things that we are pretty comfortable. N to the power of 3, this maybe nowadays this is still doable. because of the GPU, you can do parallel processing, and but GPU doesn't help you with all the exponentiation. Okay, it still cannot help, cannot solve them comfortably, right? But n to the cube, maybe, okay. But we will say that for tractable, we will say practical versus unpractical. Practical one, we means anything n square or below or better. Okay, or better means below lah. N to the power 1 point something, n times log n. These are below n square. You can see the actually you do actually you also see this for example here, this is a table. N to the 1, that's the best you can do. N square, it's a quadratic. It's already, when you have 1024 size of n, which is a small number, right? 1024, it's only 1000. All right, 1000, when you plug it into 1024 raised to the power of 2, you get 1 million already. All right. If it's NQ, you got 1 billion. This is worse. Okay. So this is already near the area that it's not really solvable. It's not really practical in a way. But with the GPU, this is still possible. Okay, so we are talking about how good is your solution, right? So first you get it correct. Next, you want to know how good it is. We talk about the time and the space. Okay, once you have solved it, still there's a question, right? We still sometimes doubtful about ourselves, our ability. All right, so how do we know that you have done your best? Okay, you know that if you are practical n to the square, you are or you are happy, but still is n square the best that you can have? All right, so this is also still some doubt in us. Okay, uh, here are the two words that you can note. One is that every problem that you talk about, okay, every computational problem, for example, if you want to find a particular number, 5, in a collection of 100 numbers, then you have no choice but to go through every single numbers, correct? And then if you have to go through every single, if you don't go through every single number, then the adversary, the guy who trying to fool you, can purposely put the 5 at the location that you don't visit. Okay, so then it can fool you. So that kind of problem, if you have 100, you got no choice. You must spend 100 check to find the number you want. So a problem itself always have a base that you must spend the amount of time. This is called the lower bound. In our case of the example of 100 items, then we have to go through every single item. All right, so that is the lower bound. Okay, so a lower bound is with respect to a problem. And then when you find a program, you get an upper bound, meaning that you have already proved that you can for sure solve the solution with this and much at best, at worst, this amount of time that you needed to spend. Right, so there's this thing called upper bound and the lower bound. Lower bound usually refer to the problem itself. The upper bound is your program that dictate or set the stage that you need to spend the time. Okay, let me just finish with the last point. Yeah, I did mention this. There's a trade-off between time and space. All right, computer science is algorithm plus data structure. The algorithm is dealing with pretty much the time, and the data structure, if you choose the data structure correctly, pay for it, then the algorithm may be less needed time. All right. So, but once again, you cannot have the storage in the world. You must have some constraint on the solution, on your space that you can get your hand onto. Okay, I'm done with the first half. I'm going to talk about counting next. Any question? Yeah, okay, give me a check. Okay. So in review, usually I talk all the time. In recitation, I will try to engage you. All right. Review is pretty much giving you big pictures of things, and so I I should do the talking. Okay, but I will see how it goes. All right. Now, why counting suddenly pop up here? Okay, this is out of nowhere, right? Counting is actually a subject in 3-2. It's a subject in 1-2-3-1. All right. This is subject in 1-2-3-1. Why counting is here? Because when we talk about time and space, we are actually doing counting. Right? We count. Oh, this particular execution do how many times? This execution does it n time, then n minus one time, then n minus two time, and so on. Already is a simple case, all right? You can simply add it out 1 plus 2 plus 3 until n, and that is the total time you need, which is n squared. Okay, but there are other examples of time which are very convoluted. As you get more advanced study, you will see it. Ultimately, everything here is under counting. Okay, if you know how to count, then you will be able to do a better job in analyzing the time and the space needed. Now, so counting is a very difficult subject to many of us, including myself. Why? Because we often undercount, we often overcount. All right. And these are the two things we must avoid. All right. Must recognize. Once we can recognize them, then we will, if you undercount, okay, try to find out where you forget to count. If you overcount, okay, then undercount means that there's something to be counted, but you forget, right? It means that you missed it. Overcount means that something to be counted, you counted it more than once, right? You count a particular item 2 times because you come from this way, come from another way. The other way also reaches the same thing, but you didn't realize it. So when you're overcounting, you try to subtract away things. All right. So this is adding, this is subtracting. And then the next statement that's very equally important is that you have more than one way to get your answer. This is why I posted already in the forum about give me another way to do the house of card counting. Okay, I want to solve this house of card for you to see in the next 20 minutes. Here, let me call my slide first. All right, these are the 3 points. Do not overcount, do not undercount. There are more than one ways to count the same thing. All right, question A is a warm-up. What does it mean? So in practical exam, all right, it's often the case. I'm one of the this wasn't my paper. This is 2018. I joined the team only in 2020. All right, but 2018, all these are relevant. Okay, it's always in parts. There's a part A, there's a part B. Okay, and then there could be a part C and so on. Usually, it's without fail, and most of the time. Part A is the easy thing to warm you up. Then part B come to really test you, okay, on the thing. All right. So usually you should be able to attack A straightforwardly, and then B you may need to think a little bit more. All right. But anyhow, so our practical exam is still a far. It's in end of May. So it's too far away, but still it's worth looking at this. So this house of cards it looks like this. You stack cards up. You started with 2 cards, the top 2 cards. Then this is called level 1, okay, of height of 1. And then you add another card below this card, and then form it. Then you put 4 more cards. All right, the 4 more cards. So the top part here, you see. Likewise, you add 2 cards here to make it into the top. Then you add 6 cards below. Right. Then from the level of height of 3 to the height of 4, you simply take the height of 3, add 3 cards below, and then add 8 cards below it, and then to get the full height of 4. Likewise, for height of 5, and you know how the height of 5 will look something like this. All right, this is height of 5 on level 1, 2, 3, 4, 5. Okay, at the bottom level, there is no cuts. You see, the bottom got no cuts. Okay, so all the cuts are marked in line. Okay, so question number 1. Question number A tells me to implement the function number of cards which take a non-negative h and return the number of cards needed to build power of height h. So you can see the answer for h equal to 1 is 2. H equal to 2 is 1, 2, 3, 4, 5, 6, 7. 7. H equal to 3 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15. Now, you can see easily this is a recursive structure. So from level 2 to level 1 to level 2, you add 1, that means the same level. Then you take the 2 times 2 to get 4, right? So you get 7. From 2 to 3, you just take the 7 card, and add 2, and then take the bottom 3 times 2 to get 15, and so on. So this is straightforward. So we can write that. All right, so this is number of cards. If level n is 1, or I should have used h. All right, it's 1, then you return 2. And otherwise, you return the number of cards at the previous level plus the number of cards needed to form the base, okay? And then the needed card to make the last level, okay? So it's 2 times of that than this. All right, so you can try it out with the test. So there's a test here. All right, so 1, 2, 7, 15, and so on. All right, 2, 7, 15, 26, and so on. All right, so this is done. Okay, so this is a simple recursive structure, and you identify the base case, and then you do the addition. So this is doing the counting, and we do this count. We only covered those things already there, but we have added this card and all this below card. All right, so we needed to add. So this is basically undercount. This by adding this to make it correct count. Okay, you needed to add these two to this undercounted to make it correct. Okay, so this is an easy question. The difficult question is here. All right, so in this regular structure, right, this is regularly, you can see that you can find triangle. This is a small triangle, small triangle. This triangle of size 1. This triangle is of size 2. And you can see size 3 triangle looks like this. So for this 3 level, a height of 3, there is no size 3, right? Size 3 will require cuts at the bottom, but you don't have, right? Only size at height 4, then you can find one big triangle that looks like this. All right, so your job is to count the number of triangles from size 1 all the way to size, in this case, size h minus 1. Okay, so what will be? So to do that, we needed to understand. So from height of 3, this is height of 3, this is height of 4. This height of 3, you see that there are 2 types of triangles. One is a upright triangle. This is a blue color. The other one is an inverted triangle with a green color. So because you're counting the total number of triangles, and you can count them separately, and then you can then add them up together. This counting upright triangle is undercounting all the triangles available. Counting inverted triangles is also undercounting, but the undercounted part is simply because of missing of each other. So the sum of these two will give you the solution. All right, so I can plan out my code. So define number of triangles H. All right, if the H is equal to 1, return H is equal to 1. H is equal to 1 means this, you don't see any triangle at all. So this will return 0. Okay, else. All right, else, what do I have to do? Now I want to count them separately. So I want to count upright triangle. And then I want to count inverted triangle. And then I want to then return, by recursion, I want to return number of triangles H minus 1. This is using the previous counted part and plus the missing one, all right? Missing part, all right? So what are my missing part? My missing part originally is I initialize to 0. So I wanted to count the missing one. So let's try to understand this missing thing. Okay, so you saw the 4 level. All right, now I will show you 5 level. So I want to use 5 level to use 4 level counted numbers to supplement to solve it in that recursively. So you can see that in this 5 level, I'm drawing the 5 level. It has one new 4 level triangle, which wasn't there in the 4 level, which wasn't there for the house of cards of height 4, right? Because there was missing this guy. So in level 5, I actually added this, and the 10 cards below as new card. So I can find this new one. So this is missing in the counting of 4 levels. Beside this big one, I also can find this is of the original one, the original size of 3. And what is new here is this one. This is a size of 3 newly created because of these 3 cards down there. Likewise, this is another one newly created because of these 3 cards here. So I originally have one size 3. Now I have 3 size 3. So I undercounted by 2 of them. All right. So the 2 more next biggest with this. And you can do the same reasoning. You can see that this is a new size of 2, new size of 2, new size of 2, and there are just 3 of them. All right, so these 3 are new because these are the new cards at the bottom. And this is new one, new one, new one. So there are 4 of them. So this is so we miss out when we count 5 level, we miss out from 4 level with this big triangle 1, with this 2 size of 3 triangle, with this 3 size of 2, with this 4 size of 1. So this is undercounting in this manner. Number of size h minus 1 we miss out by 1. Number of size h minus 1 we miss out by 2. Number of size h minus 3 we miss out by 3. And that number of size h minus 1 we miss out by 4. So we just need to add this number back to the calculation. So what it means is that in my code, all right, the undercounted upright triangles I can do it with for I in range 1 to h number missing part equal to missing part plus I. All right, you remember I add 1, add 2, add 3, add 4. So until h minus 1. All right, this is a h minus 1. All right, so this will take care of what I miss out. I didn't manage to count. Right, and now I will do the same for my inverted triangle. Okay, so this is my upright triangle. My inverted triangle, how does it look like? So this is newly created because these 3 cards are all new. This is also new. This also new. This also new. So I have four new one that wasn't in level 4. So I needed to add these four them back. All right. So number of size 1, it's h minus 1. Now what about size 2? This is new because this card is new. These two cards are new. Okay, so this is legitimately a new triangle. This is also new. And that's all I have. So two more next level. Number of size 2, I miss out by h minus 3. Okay, h is 5. 5 minus 3 is 2. This is size of 3. Oh, I don't have these two cards here. So this is actually 0. All right, 5 minus 5 is 0. And that's all. Okay, so if you have higher level, then you may have more. But anyhow, so this is what we undercounted. All right, so I needed to add them back. How do I add them back? I will use this loop again, h minus 1, starting from h minus 1, 0 until minus step of minus 2. And the missing part is missing part plus, in this case, I also. Okay, because my I is h minus 2 until 0 in this case. All right, so this is so this guy undercounted, and by adding this, which I carefully count it upright and carefully count the inverted, then I add them to here, then I should get my correct count. All right, let's test it out. All right. Okay, 027. Let's see the. All right, 027, 17, 33, 57, 19, 134, 190. Okay, so we are done. All right, so this is following religiously in the way that we reuse the counting, and yet we undercounted, and then therefore we add it back those undercounted. Okay. All right. So here I pretty much solved the problem. I will quickly talk about what I posted in the forum. Uh, as I said that there are more than one ways to count. So just now I counted it by employing the recursion of one level lower. But there's more than one way to look at that recursion one level lower. So here is also one recursion one level lower. So I could have counted this, right? But if I do that, then I miss out all these cards. I didn't count this card. Then I try to cover them. I will use these cards. All right. So I have counted one level smaller, one level smaller, right? But in doing so, look, there are some overlapping, right? Some of these guys here have been counted here and yet also counted here. So this is overcounted. All right, I must subtract away. All right. So I have to subtract away this also. And you see that, there are still three cards up here. These three cards are not counted at all because this actually itself is a upright triangle. This itself is actually a inverted triangle. So I miss out at least two already. So what else do I miss out? You go and find out yourself, and then you can see the forum. All right, so these are overcounted, and then this is undercounted. All right, so we have, in looking at this is a good exercise to see that another way of solving the problem, and there's an overcounting part, and there's an undercounting part. All right, so this is what I wanted to share with you about counting. Remember these 3 points. Do not overcount, do not undercount, and there are more than one ways to count things. Okay, I want to use the last few minutes to talk about one last point. There's always the question about, okay, let me just unmask this first. Okay, these are the same. So if you count A, you count B, then if you overcount, you need to subtract away A and B. Okay, so this is testimony to that. All right, so this is another important thing that I needed to tell you. So some of you taking this class, you may be scared that how much mathematics we actually need. Um, Actually, the mathematics that you need may be coming on your way. Still, some of these are really high school mathematics. Particularly, we will want you to at least understand AP and GP. Okay, arithmetic progression and geometric progression. Arithmetic progression is always one number, next number, and so on. The number differ by the same amount. Right? In this case, 2 is 1 larger than 1, 3 is 1 larger than 2, 4 is 1 larger than 3, and so on. So you should know how to sum up this kind of thing. This is actually the sum of an AP is always the first item plus the last item times the number of items divided by 2 because you pair them up. Okay. The front 100 plus 1 is 101. 99 plus 2 is also 101. They're always the same. So the number of terms is n divided by 2. So this formula you have to know. Okay. The next formula you have to know is you try to sum this up, a times r, a times r squared, a times r cubed. It comes in the form of like this. 1, a is 1, r is half, so you got 1, half, then r squared become 1/4, r cubed become 1/8, and so on. You should know how to sum this up to be less than 2. Actually, the sum is straightforwardly, the sum s it's of all these number is the same as r times s shifted every one by 1, right? So you get this formula, and you will subtract s minus r times s, you get this, and the answer is this, a times 1 minus rn divided by 1 minus r. So this formula you have to know. And other than this, today's forum, you will see L'Hopital's law or L'Hopital's rule, and this kind of thing a little bit more advanced, but I don't mean that you have to know them. Just that you to solve the problem that I posted there, which are kind of like ECA, you will have to know that. Okay, I'm done with the review. So the today's review is giving you some hint about how good is your solution, and we will talk about that shortly at 8 o'clock. Any question? Quick one I can answer. No? Give me a check, then we take a break. Okay, great. I will off the video first, and then we come back at 8 o'clock. Okay, 8 o'clock. Let's get started. Recitation 2. This is on lecture 4. So recursion, iteration, and orders of growth. All right. So this one, a bit of the mathematics here. You have to understand. So here we wanted to get our program. As I said before, we want to get it correct. Then we talk about the efficiency. The efficiency we means the time and space. All right. For time, we actually using a stopwatch may not be. You may get something like this. All right. So or even worse, something like this. So this is the function fn. We wanted to talk about our function fn. This is the growth, the growth order of growth of our function, the time that we analyze our code. But we want to use a more simpler function, which is gn. Usually something looks smoother, right, to capture our function here. So instead of the stopwatch, we actually, okay, we can also use stopwatch as you will see in the next week or so when I talk about the review. But we, in general, wanted to characterize our work, our program with a function. In this case, we want to use a nice function, and the nice function will look something like this: gn equal to 1, in this case, gn equal to log n. This case, gn equal to n. This case, gn equal to n log n, gn equal to n squared, gn equal to 2 to the n. All right, so our gn is all these kind of numbers here. So there are two notation here. One is called the theta. The other one is called the big O. The theta is a big O with a horizontal bar. The big O is just simply a big O. There's a small O also. The small O is usually means the below. Big O means on top. All right. So there are two symbols that you hope that you are not so frightened away. That exist. That means that there is something there. If and only if. This one is familiar to you. So what a function, it's called theta, another function. Basically, this is a function which could be the ugly one. And it's called theta, this function, meaning that if and only if there are three numbers that you wanted to keep, k1, k2, and n0. k1 is multiplying with the gn is here. So k1 is a smaller number that multiply with the gn is always less than fn, okay? And k2 is a bigger number. Usually when multiply with gn, it's going to be larger than fn. Basically, whatever number you have here, all right, you take a vertical line. You see that k1 gn is below fn and k2 gn is on top. So this is the lower part of it and this is the upper part of it, okay? So if you can find a gn to be theta to satisfy this formula for n greater than n0, this n0 it's some number that we start from here and then for all the numbers from here onward. Anything below we don't care. Why is that so? If anything below, it may fail. The gn times k2 may gn times k1 may not, for example, you see the fn, it's below the k1 gn, but we don't care about this. These are things which are small in size. So n0 represent the size that we want. Anything larger than this, then it's of interest. Computer program is designed to solve large problems. So n0 is some number large enough to make sense for this function to behave within these two functions. All right, so n0 is our choice. You can choose the n0 here. Of course, n0 here also work. All right, if you choose n0 at some point, if you further down, it should work too. But below it may not work. Okay, so anything above for sure it work. All right, so this is called the theta. This is an exact bound in a way. This is exactly bounding it. That means that this guy is tightly within these two functions. Okay, these two functions are actually the same function with a difference in constant only. Now, why are these constant? So these are constants are that k, it's k1 and k2, it's for fairness. So remember I told you that your computer could be newer than mine, which is 3-4 years old. And when you run your program in your computer, of course, it's going to be faster than mine. But that's not significant because how fast can you be? You can be only a constant bit faster than me, right? And so K is to undo this particular thing, basically to equalize out the poor versus the rich, right? The poor and the rich are no difference. Okay. And then N0 is for scalability. It means that we don't care anything below it. We only care things on top here. All right. So this is what these two function usually for this course we talk more of the big O, all right? And if anything is theta 1 is also big O1. Anything which is theta log n is also big O log n. Basically, we hardly pay attention to the bottom one. We usually pay attention to only the top one, right? So you see here, Fn is equal to big O Gn if and only if there's a k and n0 where this part, which is the behind part, right? Not the front part. The behind part is satisfied for n greater than n0. Okay, so this is what we wanted. And if this kind of function is called constant, this is called logarithmic, this is called linear, this is called n log n, this is the usual one, and quadratic, and this is exponential. Things here are what I meant by polynomial time. Actually, this is a constant, and these are tractable, and these are practical thing. This one is intractable, this is exponential. Right. So this is what a little bit of this theory. You will learn this function thing in the 1231 course, but we needed it already here. All right, to be able to talk about how good or how bad our code is. Okay, any question? You okay? Give me a check. Okay. All right. So for today, I'm going to go slow. All right. Here, there are tricks that will tell you, all right, you can ignore this, ignore that, and so on. Your life will be very fast and quick. But of course, these are shortcuts. Huh? I don't want to do the shortcut for today. I will do the normal way. So here are what the 3 points that I should take note first. All right, first of all, we take multiplication, division, and addition, subtraction as O of 1. Basically, even though multiplication and division, as you know, is harder to do, even mentally, when you work on paper, it's addition and subtraction are much easier. But what's the difference here? This guy, it's maybe 100 times more than this guy. So this is O1 versus O100. Okay, O100 is the same as O1. All right, so multiplication, no difference from addition. Division, no different from subtraction, and also no different from addition. Okay, so this is what we will do. Every operation dealing with multiplication, divisions, addition, and subtraction, they are all the same. All right, the next point is this. This point I need to put it there so that next time when you come back to this class, you don't blame us that we are telling you the wrong thing. In actual fact, when we talk about all these functions, this n that we talk about, it's usually the size of the input. The size of the input is not the same as the input number. Okay. For example, when you do primarity test in the later part, all right, primarity test, the number n is not supposed to be used, but we do use it. So whenever we talk about complexity or we talk about the order of growth, all right, the word complexity sounds complex, huh? But order of growth, but it's the same thing. The complexity, we use n. Whenever you tell me n, you have to tell me what n means. Okay, so I make this an habit because without telling us what n is, whatever you give us is useless. All right. So when I say that, actually, when we talk about polynomial time, it's the word pseudo means fake, right? Fake polynomial time. I don't want to go into too much detail, but I can point you to the website. All right, this is a pseudo in the Wikipedia. It's a pseudo polynomial. Actually, it's not really polynomial, but we will as if it is polynomial. All right, my priority test is here. You can read about it. All right, so take note of this next time when you come back to look at when you study some higher level course, the definition will change. All right, you're supposed to get polynomial is polynomial. It's not supposed to be pseudo polynomial. But here we allow you to use pseudo polynomial. The third point I wanted to make is that today I'm going to do it step by step. I'm going to ignore this kind of shortcut, and hopefully we learn something from here. Okay, so first question. All right, so here also say that. All right, your unit n it's whenever we talk about the growth, the n is the size of the problem. Okay, and very often when computation you calculate factorial 5, n is 5. Okay, so you n is the number inputted into the factorial routine, and we calculate how long does it take with respect to that. Okay, so this one will need you to pay attention as you move forward. When you see many more programs, you will then realize what is the end that you're talking about. Okay, so first question. Let me engage you. Write a recursive function called order size, which take an order and return the number of combos in the order. For example, order size 237 is 3. Can I see some posting in the chat box? How you solve this? Okay, try to post it there and then I will give you mine. Okay. 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 Okay, good enough. I have enough. I have pretty good. Okay, so this is what we have. Okay. This is one of them. So this is order size order. You just make the order into a string and then length. Okay. So how much time is this? Let's try. Whoever give me this. Uh, Jonas, Ching, Jonas.
Hi, yes.
Hi. Okay. How much? I think this is similar to yours. How much time is this? So whenever you write a code, right now it's time that you can then practice what is the time and the space.
Uh, I'm not too sure about time, but I think space is like bracket 1.
Bracket one. This one. You mean this?
Yes. Yes.
Oh, why? Why is this one? It means constant, you know. That means that no matter how this order comes in, I only need one variable, some constant number of variable. Is that what you mean?
Actually, to be honest, I'm also like not very sure on this.
Yes, we're new to this, so we are not sure, but it's okay. You just try your best. Let me try to see whether we can get some hint out of this guy. Um, okay. Let's see what happened to this. Okay, so this guy doesn't tell me much, but this is a Python tutor. Python tutor is a visualizer. It's good to for beginner like us, okay, to see how are things organized in the computer. This is the program you have. This is the part of the code that it show how the thing are executed. All right, this simple example will just simply go to, you just go inside here and then return this statement. You go inside there, this is a function, it's a size. The order is this value, 1, 2, 3, 4, 5, 6, 7. I simply calculated it to give you 7. So nothing, you can't tell anything. But we'll see something like the factorial later on. This factorial we can see more. All right, we'll get to that. All right, just on this thing, the tricky thing for us is that when you do string order, do you have to include any space, Jonas?
Uh, I believe you do.
Yeah, we do. Yeah. So you must take this order, which is integer, some numbers, make it into string. So you have to include the 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 amount of the number of digits here. All right, for sure. Not to mention that actually this guy, I don't know how he works. Intermediary, maybe some other space also needed. All right, so the space should be O of k, maybe we say, where k is the number of digits in order. Okay, would it be more accurate?
Should be,
Okay, next. So we need to spend this amount. We need to keep it, right? We need to, for example, uh, okay, maybe I do another way. 10. Basically, this 10. This is string order. I'm doing the same program, right? I just simply take this 10 and then do this. Now you see the 10 is this. So I incur this amount of space, all right? Then I get the value 7. So how much space I incurred? I incurred this one, which we already accounted for, O of k. And this return value, this is only a single number. So this is constant. So the space now is O of k. We can accept now. Okay. Now what about time? Jonas. So what do you think time?
uh, it's like based on the number of digits also, because it needs to calculate one by one.
Mm-hmm. Yeah.
So
Uh, so the time, maybe this string thing will cost me the time. All right. The string thing will cost me the time where k is that. And plus, I also need to do length, right? Length, right? How much is this? The length, which is an operator, right? So I dig out the length of string time complexity in Python. The time complexity of finding the length of this using built-in length function is O of 1. Okay, so I'm doing O of 1. Okay, so the time is OK plus O1, which is OK lah. All right. Now, you're going to encounter many of these kind of built-in function. There is a table you can refer to in Python, time and space complexity reference. The time complexity for the list, which we will use subsequently, and set. All right, so these are the operator, dictionary, and so on. All right, so I just give you the you have to, at time of doubt, you have to check the web and see what is the time. So I get this one from the web. Now, why is this length only constant time? You can search further. You can see that actually, for me to be able to tell that this length is actually constant time, it's uh it's because this is trading of time, trading of space for good time. Okay, because the system must have kept the temp as a number at the same time. this number is not just simply this number, but also some attribute, right? We call auxiliary or we call metadata that will keep about this guy, that there's a 7 digit in there. Therefore, length of this will simply give you O of one time. Otherwise, you can't get that. You may have to go through one by one. In that case, it will be OK plus OK, if you don't have that. Anyway, I will leave you to discover. At our level now, I should say that some of this stuff you have to be taking it carefully. It may not be true, depending on the app, the implementation. All right. So, but we, as much as we can, we follow it. But do question some of this stuff that if it's not correct. Oh, I do see another solution. So things like this. Okay, thank you, Jonas. Let me move on with someone else. All right, so this is another solution. Order equal to empty order, you return 0. Return 1 plus order size, order divided by 10. That is to strip off one integer and so on. All right, so what is this time complexity? Let's try. I try Bruce. Bruce, you give me this. I see your solution is that.
Hello, can you hear me?
Yes, I can hear you.
For time, I will say this is also okay, where k is the number of digits. And for it's okay then. And space is also okay, where k is the number of digits in order also.
Okay. All right. So this case, you will go to the Python tutor. Oh, empty order is it's not defined. What is my empty order? Return still. All right. So you see that the footprint of this code is such that it looks like this. You have order. Order is this value. It recursively call this guy order. Order become one less and one less, one less, one less, one less until here. And until it's 0, you return 0. Return 0, return 1, return 2, 3, 4, 5, 6, 7, and the answer. Okay, so this is the basically this code needed you to keep track of 7-digit number, then 6-digit numbers, and 5-digit number, and 4 and 3, 2, and 1. And each digit you can take it as O1, and therefore is okay for your space. All right, thank you, Bruce. Okay, here is another ridiculous one that I got yesterday, which was wrong, but today I fixed it. I want to give it to you. Right, order size number, if not number, return 0. Okay, so maybe this. I check whether my number, the last part is equal to empty, else I return this. I do the integer, the string, and so on, which I think, yeah, I see. Maybe I think Jonas, yours is quite close to this also. Okay, let's try this. All right, so you can see that fortunately this string wasn't being kept anywhere because it's converted to integer, and therefore the size looks still the same. So this is still the same as this guy. All right, we can try it out. Okay, that's A. B, write an iterative version of order size. Can I see some posting in the chat box? Can you post iterative version B? Okay. All right. Okay. So let's see. B. Okay. All right. I see there's quite many of you use the string conversion and then take the length. Try not to use that. Converting from integer to string, it may looks it's not quite natural. I mean that it's not easy to compute, and you do not actually need to use it. So let's see the solution ahead. All right, you don't need it. You don't need those kind of conversion. You simply have the count is 0. This is over 1 for time and space. While the order is not equal to empty order, we needed to do this because we reuse the code. Okay, remember, the more code that you write, the worse, the more you have to test. Of course, this case is simply a 0, but still, it's always a good practice to put things by some function that you use. Then the order is order, take away one of them, then you add it, and then you return the count. All right, so this is also O1, this is O1, and this is looping through n times, where n is the number of digits in the order. Okay, so this is part B. And part C, write a recursive function called order cost, which takes an order and returns the total cost of all the combos. I think the value of this question to me is that if you know how to do part B, then part C is the same structure. So you should always see that so we can reuse things from the whatever we learned already and just change it. So part C, it looks like this. So the order, so basically you take from part A right here, right? The order size become order cost. So this is the order size. I will change it to order cost. See, right? So if the order is empty order, again you return 0. Otherwise, you return this one, which is the count, become combo price of the which combo is the order, the one you take out one of them. Okay, then order size become order cost. So I need to change this to cost also. And the order remain and the 10. So I'm just copying from A to here, and I change the calculation for him. Just change the name of the function. That's all. So because this guy is constant time, all right, if you check it out, then the whole algorithm still remains the same as before, the same time. What about D? D, again, the same thing. D is to write an iterative version of the order cost, which the order cost, the iterative version of this, I can convert it to here. Right, so this is the cost. And then instead of count become the cost. Instead of count is the cost. The count is the cost. Count is the cost. And the one is simply the combo price, the order divided by 10. Okay. But there is a catch here. Yeah, the value of this question is that if you simply copy here, it fails because this order has been modified to be a different order. So when you take the remainder, you are at the wrong order now. So this has to be at the back. So this has to be the order equal to order divided by 10. And on the other hand, when you're doing it in B, it makes no difference. This still works the same. All right, by removing. But when you're doing the calculation using that value, you have to be careful. All right, so that is the value of this question. So for each of this kind of question, you have to ask yourself why such a question is there. And hopefully you can question even more, how do I do some other thing not explicitly asked in the question? Okay, E is something I can leave it to you. This should be easy. Yeah, if you use string, then there's nothing I can talk about. All right, so question 1, any question? Yeah, okay, then I move on to question 2. Okay, question 2. Question 2. All right. Give order notation for the following. So this the order of growth 5n squared plus n. So let's try. Elvis. Elvis.
Yes. Can you hear me?
Yes. Okay, what is it? 5n squared. What is it? Plus n. This is equal to order of what? Do you try?
Hold on.
Mm-hmm.
Not quite sure.
Okay, let's try. That means that we want to, this is my f, function f. I want to get my g here. Okay, so you will consult this theory. You should be able to, this f is given 5n squared plus n. I want to simplify it to be something looks like this. Okay, so let's try. So this is 5n squared plus n. This is the same as 5n squared plus n squared, or rather that this is less than this for n greater than what? Elvis. Can I write this? This function less than 5n squared plus n squared. I change the n to n squared for n greater than what? This should be straightforward, right? What number you can put in here? N are integers. It's 0, 1, 2, 3, 4, 5. What number you want to put here?
6.
6 also work, but 1 is enough. All right. When n greater than 1, the formula, this will fulfill. Okay, basically 2 onwards it works. Okay, and this is the same as 6n squared, right? 5n squared plus 1n squared is 6n squared, correct?
Yes.
Okay. Next, now I have, you can ignore constant, ignore lower order term. I didn't ignore lower order term. I just simply show you how I can get rid of him by putting a plus there with a bigger number and so on. So this is equal to this is your F, right? What about my G then? My G can simply be the same as the F, right? For N, for K equal to what? And N0 equal to what? All right, so for you to put a function Fn into a Gn with a big O, you need to find me K and N0. The K has to be that whatever K that is here, the Fn must be smaller than K dot Gn, K multiplied by Gn. Whatever N0 is here is N must be greater than N0. All right, so Elvis, so what should I be K? What K can I choose to so that the Fn is always less than the K times Gn? This is my Gn. Yeah, you are confused still.
Sorry, I'm really very confused at the moment.
Okay. All right, let me try someone else. Okay, you just follow first. Cohen.
Yes.
Yes. So what should I choose my K? All right, I want to fit my Fn. My Fn is 6n squared. This is Fn equal to 6n squared. Okay. My Gn is n squared. Gn is n squared. So for me to write like this, I need to find myself K and N0. What is my K? It's very obvious. Huh? You're also confused. Huh? What's my K? Or any one of you? Hello? Yeah. Okay, maybe I'll show you the picture.
Sorry, is K just 6?
Yeah. K is just 6. So let me show you the picture. Who was it? I'm telling you my Fn is like this. Right? My Fn is 6n squared. I wanted to find my K2. Maybe this picture is okay lah, just this one. All right, my K2. I can choose my K2 to be exactly the same as Fn. So my K is 6. What about my N0 then? Who was that just now? Who answered?
It's Me co-Kaiser.
Oh, Kaiser. Okay. What will be the n0?
Well, since we've chosen a k that makes k times gn equivalent to fn, then the expression should be true for any n0.
Yeah, but you must follow, right? This is the formula from here to here to here. You already have n greater than 1.
Yeah, well,
So,
I guess I'll just go with like 2, I guess. It's a decent number.
yes, 2. Okay. Or any number greater than 2. Okay. All right. So this is how you get this answer to be this. All right. So 5n squared plus n is indeed O of n squared. If you follow the implication, ignore constant, ignore lower order term. Basically, you ignore 5, the constant. Ignore lower order term, you ignore n, because n is smaller than n squared. Okay? That's it. You get O of n squared. All right, let's try another one. Another one is okay, n to the power of 0.5 plus n. So what is this? Let's try Dylan Leong. Hello, are you there?
Hello.
Yeah. Okay, great. What do you think this is?
O M.
ON? You mean this? Is it?
I think so.
Okay, you are right. So in this case, but if we do it slowly, so slowly as in like above, this is correct. Okay, but if we want to do it slowly, it should look like this. Because the 0.5, n to the power of 0.5 plus n, of course, is smaller than n plus n, or n greater than 1, right? And this it's equal to 2n, okay? And because this is 2n again, this is your, here it means that fn is equal to 2n. What is my g? My g is simply n, right? For k equal to what? Who was that just now? Oh, Dylan. K equal to what? K
K equals 2.
2. All right, even 3 also can. Okay,
Okay.
2. And n0.
E0 is 1, isn't it?
No, but cannot be 1 because it's larger than 1.
2. Okay.
Okay. All right, so this is how it works. These are simple cases. So okay, last one. We'll see. All right, 2C, let's try. Okay, got win. You're the first one to attempt.
Prof, I
Hello.
think this one, the complexity will just be 3 to the power of n times n squared. So it doesn't
Okay.
change.
It doesn't change. So you think this is this? All right. Is that what you
Yeah,
mean?
correct, Prof.
Okay. Now, okay. So of course, this is if I nasty, right? This is also equal to all to the power n to the 100. Anything wrong? Godwin? Is this okay?
I think it's okay, Prof. You just have to adjust the number of
Correct.
K and
So
N0.
this is also okay. But we don't like this. All right. Why? Because this is not. The word is tight. Okay. We want something tight. So for example, when you look at the picture, all right, when I draw this curve on top of him, of course I can draw another curve even bigger on top of him also. Surely I have many more I can do, but I don't like those. Why I don't like those? Those are not tightly holding on to this guy. I want whatever as much as we can hold on to him. That it's more like smoothing out all these small little wavelength thing that we wanted to capture in a simple function. In our case, the simple function is n squared. N to the 100 is ridiculously big, and for sure it's correct, but it's not tight. Okay, so you always look for something tight, and so this is correct because this is tight, and of course you can also see that nothing wrong with this. All right. Yeah, but we don't like this. For the same reason that it's not tight. Now, then come back to you, Godwin. Is this tight? Or can you do better than this? All right.
Think
This
can
looks
do,
ugly. Huh?
think can do
This look
better.
what?
Think can do better.
Okay, how?
If you want to make it tighter, maybe reduce it to 3 to the power of n only.
3 to the power of what?
N.
Or you mean make it to this? Is that
Because
what
I
you mean?
assume, yeah,
Okay. Now this is a tricky question already, huh? If you do this, what is your K and N0? Can you find?
well, the key I'm not sure.
Yeah, any one of these you're not sure you did. All right. I bet that you cannot. Okay. Because this is going to be a function below him. Whenever you choose an N0, this function is going to be below him. That means when you look at the picture, if you choose 3n, this is my Fn. The Fn is going to be, at some point it's on top, but at some point it's going to be below. After that, it's going to be low. As such, whenever you choose an N0, it fails. It will fail to be like this. It will fail to give you this condition. All right, so this case is not possible. All right. And then I'm going to post this in the web to check for you. So this is wrong. What about this? O of 4 to the n. Is this okay? Godwin.
I don't think so.
Oh, you don't think so? Actually, this work.
Okay.
Oh, this actually work. Okay. This works, but this is not good. Why now? You should know. Why?
Because it's not tight.
This one is even. So just now your choice is the best. Your choice was your choice was O of 3n squared. Why? Is the best. Why? Because if you look at the chart again, 3n squared is exactly on the same as fn. 3 to the n is below, and 4 to the n is actually on top and is very far away. 4 to the n even further away. All right, so this 4 to the n, it's correct, but it's not good because not type. Okay? And how do you show that? I will post it after this lesson, that you can show that this one grow much faster than this guy. This guy grow much slower than this guy. This guy, of course, grow at the same rate as this guy. So this is the best. Okay? Godwin?
Yeah, can.
Okay. All right. So I see that you guys need some more practices on how to deal with this kind of stuff. Of course, here the rule of thumb, things like this, implication, ignore constant, ignore this, blah, blah, blah. It's what I work it out for you to see that why you can ignore constant, because the constant is absorbed into the K. You can ignore the lower term because the lower term can use a higher term to absorb him. All right, so that's why this kind of statement is there. For a sum, you can take the larger term also. All right. See these two guys, the sum, there's a sum here. You can take just n, the larger term. For product, multiply the two terms. This is the product. Unfortunately, you cannot absorb any one of these guys. Of course, this guy is smaller than this three there, but you cannot ignore him completely. You cannot move in. If you move it in, you get 4 to the n. Right, and 4 to the n is not as tight as this guy, which is better solution. All right, so all these are things that you have to watch out. You can try some more yourself. Okay, any question? We are done with question 2. You okay? All right, and in the forum, I posted this. I think there's some discussion already ongoing. I posted this, and you needed L'Hopital's rule to check it. Okay, who is better? Log n versus this guy. Who is better? This is L'Hopital's rule. You can also use it to check here. All right. You can check for this guy and check for this guy using L'Hopital's. All right. Now we are at question 3. Okay. Question 3, factorial n equal to 0, return 1, return n, and factorial n minus 1. I have it in the Python tutor here, factorial. All right, so if you use Python tutor, you type in this, then you visualize. Once you visualize, you finish step 1 of 26 because I print this. So if you try it, you will see there are this many steps. Okay, and these are the footprint of your storage. And you can see, and you can then analyze how it is. I want to show it to you directly, step by step, without the Python tutor. Okay, before that, maybe you post in the chat box what is the answer. Let's see. What's the running time? Can I see your running time? Question 3. Anyone post it? Don't see any. Okay, time ON. When you say ON, is a running time or is it space or what? Okay, space ON. Okay. All right. Where N is the input number N. Yeah. Okay. So let's see. Oh, just now I forgot to show you the various curve. So O1 is here, ON square is here, ON cube, ONN, and so on. This one, it's the talking about the steps. If you have N cube, you already need 1 billion, right? If you have N square, you have 1 million. If N log N, you only have 10,000. Okay, here. I'm going to do this for you. How do you get ON and the time and space? So I have the time here, the space here. Okay, factorial 5. How do I get factorial 5? I go inside here, 5 equal to 0, no. So I have 5 times factorial n minus 1, which is 4. So I have this. All right, so I have 5 times factorial 4. How much time I spent? To get to this statement, I actually check and it didn't go through. So I check, else I have n is 5 times this. So I spend O1 time. All right, I spend time to do the checking, but I haven't even done this calculation or multiplication. I haven't done it. All right, but I spend this O1 time. All right, now I want to 5 times something, but this something is not a number. I got no choice but to call the function again. The function 4 comes in. 4 is not equal to 0. I will get 4 times factorial 3. So I will get this. I will get this. All right. And again, from this line to this line, I pay for it with constant time. All right. And now you get the hang of it. So I have to do it many more times. Let me just copy them down. All right. And factorial 3, I cannot do anything. I get 3 and then factorial 2. I spend all one time again. Factorial 2, I cannot do anything. Factorial 1. Factorial 1, I have to go in again, factorial 0 until here. So I spend all one time all the way until here. And then I now can do factorial 0. 0 comes in, 0 equal to 0, I return 1. So now I can unwind. I can do, I get 1, so I pay for it. And I got this 1 times 1 to get 1, then 2 times 1 and so on. All right, next time you don't have to do this. We just have to do this at least once to see for yourself. You can either do it here or you can do it in Python Tutor to see for yourself. All right, so now I have done this. So what happened here? What is happening is that with 5 comes in, I have to do this, you count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, it's like, so the total effort is 2 times 5 plus 1. But this is actually 2n plus 1. So if n comes in, I will have to do this expansion and then collapsing to get to the answer. So this is actually I should okay, so this is actually 2n plus 1, which is O of 2n plus 1 You drop the constant, you drop the lower term, then you drop the constant, you get On. This is why you get On time. All right, O1 of this type, and you get it. Now, if you look at it, so this is time, On. What about space? Time, I say vertically, I mean that you add up all these number, you add up, of course, this 5 is just an example. If this happen to be n or 100, you will be 200 plus 1. Okay, so we have to do it as 2n plus 1, and you get this. Now, for space, how to use space? So you need to keep this multiplication because you can't do it. Then you need to keep another multiplication because you cannot do it also. So all these things are stacked up. Just now, if you have seen the Python tutor, you see that these things stack up, right? You see stack up. All right, so all these multiplication are stacked up. Actually, all the numbers are stacked up. All right, the multiplication with the number is also still constant. So this is they are all the defer operation that you're doing. All right, there's one defer here. This guy is not done. Okay, and then now there's now 2 defer, and so on. This one, which was here before, this one was before, and this is a new one. Okay, and so on. So ultimately, you need so many. This one, this one, this one, this one, and this one. All right, so for 5, you have 5 defer operations. So what this means is that, all right, the maximum defer operation is 5 for the example. In general, we will have n defer operation. Thus, the space needed is On. The footprint is the space that we needed, as you can also see from Python tutor here. All right, so this is why your time and space are both On and On, which is linear. So most of you got it correct. Okay. Next question is write an iterative version of this. Can I see your posting? Oh, okay. Okay. All right, pretty much not difficulty. So it looks like this. Define factorial n. Product is 1, starting from 1. For I in range from 1 to the last guy is n. The product times the product with the I, and you return it. So this is how. All right, so if you do it, you see that. This time you see that it's unlike just now. This part of the so-called footprint doesn't seem to increase. Just now the case you saw this, see, it increases all the way. Whereas now it doesn't. Why? It's an indication that the space is actually constant. All right, and what about the time? The time you can also look it up is here. Okay, let me do it. So the time, step 1, 2, 3, 4, 5. What do? You have I, and then you have product, and then you have the time taken. Okay. All right. So when you start with from the time step 1, at that time you actually do the initialization. This one is the product is equal to 1. right? The product is equal to 1. And then you use up this time, the time taken. Or we call this effort. Okay. And this is O1, all right? It's initialization. And the next step is I from 1 onward. So I become 1. Then next product equal to product times I. So this is 1. And the effort you do is O1 plus O1. So this is also O1. Then you go to the loop, the I become 2, and the product is 1 times 2, so this gives you 2. Again, this is also O1. Next is that I become 3, then 2 times 3 gives you 6, and this also O1 effort. And then I become 4, and product, it becomes 6 times 4, 24. And you pay for it with O1 again. I become 5. It's the last I. This is 1, 2, 0. And this is O1. So you see that the effort is simply adding up all these guys. When at 5, you actually have 6 steps. So you are actually the same ON. Right? So the time is ON. ON. Okay. The space, you see the space you needed is only I extra, product extra, only these two variables. So this is actually O1 plus O1. The first O1 is for the I, the next O1 is for the product. Oh, if you want the range also, okay, plus O1 for the range, okay, O1 for the I, O1 for the product, okay. And you have 3 O1, and this is no matter what input it is always O1 space. Okay. So so now we see that the iterative version of the factorial, it's pretty efficient. It's ON time and O1 space. Whereas the recursive version, ON times and ON space. So the space is more. All right. So that's question number 4. Okay, even though question number 4 didn't ask you about the time and the space, this kind of thing should come naturally to you now. Whenever you see something, then you wanted to check, is this good or not good? So in some sense, you can tell that O1 space is the best that you can ever do, right, in terms of space, right, it's constant. But time, if it's constant, then it's also the best. But in this case, you got no choice but to calculate one by one until you have n, provided or unless you already pre-calculated all the factorial and kept it somewhere, then you can retrieve it in constant time. Otherwise, by doing calculation, ON is the best in case of factorial also. Okay, so n time and ON space for recursive, but ON times for iterative and O1 space for iterative. Okay, we have 2 more questions. So this one, find this. Where's your question? Oh, again, we want to take the time and the space. We assume iterative factorial. Iterative factorial is ON time and O1 space, which is here. So what is this program? This program is this one. All right, Euler's number is equal to summation of 1 divided by n factorial from 0 to infinity. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 1 times 2 times 3, and so on. So if you do these things, you will get our Euler's number, which is 2.71828, blah, 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 blah. Okay. And how does this program come about? This program comes from here. E, which is the Euler's number, it's equal to the limit from n goes to infinity, En. And so En is simply this, and the limit n tends to infinity. But En, you can break it down into from 0 to n minus 1 plus the n terms, right? And this term is simply this, and this term is still here. So if you put the limit here, so the En is equal to this 1 over n factorial plus the previous guy. That's why it's 1 over factorial plus the previous guy. Okay, so if n equal to 0, you return 1. Basically n is equal to 1 term. So it's 1 divided by 1 factorial. 1 divided by 0 factorial. It's 1. Okay. All right, so you're supposed to know what is the time and space. Can I see some posting? Okay, time is On squared, space is On. Okay, so all of you say that. Okay, let's try to analyze this. Let me see what I have. Oh, I have it. Okay. All right, so I'm going to try out with 5. Again, this is the same strategy. You always do these things with small example to get the feel of it. And then you can tell if the number is big. So what happened? So same as before, we want to put it into 2 columns. All right, the time, just now we saw the time is vertically sum up. The space is, you look at it, which is the largest footprint horizontally. All right, in this case, this is the largest, which is 5. So that's why it's 5. So you notice also that the time is money, time is spent, money is spent. You cannot recover. Okay, that means that you pay for it. Whereas the space is such that you can always reuse. All right, here, this 1 space, this 2 space, it doesn't mean that you have to be 1 plus 2. It simply means that the previous one was still there. You just added another new one. So here you added 4 more new one. All right, you still reuse the same previous 4. You add 1 new one here. So it's the largest footprint is this guy. So this is the largest. And this is the space needed. Okay, so now here we want to do the same. Find E5. So this E5, you see that you actually calculate factorial. So when you go to calculate factorial, you're branching out to another function. And that function you calculate, you use some space. That space that you use actually will be free after you come back from that function. But you incur that has to account for. But the next time when you come in there to use the space, you don't want to add the space. You just simply see among all these factorial, which is the largest, you have to take that as the footprint only. We'll see now. Okay, so if you follow just now what I did, you will get all these things. Okay, let's get halfway. All right, you will get this factorial 5. You'll get this function. You pay for it O1. And factorial 5, which is not a number, you need to calculate, which is 120. All right, then plus this guy. How much time you pay for this guy? You're actually paying ON now. If this is 5, it is will be O5, but we are using 5 as an example. You know that this should be N. Then it will be ON. Next, 5E4, you expand it out to this. You pay for it only this constant time, just a simple expansion. But then when you calculate this function, you needed to call the factorial, which is here, right? You needed to pay for it. How much you pay? You're actually paying to get 24, you're paying ON minus 1. Okay. And likewise, factorial 3, you're going to pay for it. And you're going to pay for it with ON minus 2. All right. Then ON minus 3 and so on. So until the end, you get all the number. This is the number, this is the number, this is the number, this is the number, this is the number. Find E0. Find E0 is 1. So this is the number. So this 1 plus 1, get 2. 2 plus half to get 2.5. 2.5 plus 1/6 to get 2.5, whatever the number is. Okay, and all this added up. So the time is how much time is this? Okay, so this O1 come from here. This ON come from here. This O1 come from here. This ON minus 1 come from here, and so on, you know. Okay, until O1. All right. But I should then they're still below, right? So what are all these things I haven't added in? I have to do a addition, another addition, another addition, another addition, another addition. So how many addition I have to do? ON. Okay, so this will be O1 plus O1 plus O1 n times. Okay, so this one, it's accounting for all these lines that I haven't written down. Okay, and all these thing is actually simply ON. Okay, whereas this part it's alternating O1, ON, O1, ON minus 1, O1, ON minus 2, O1, ON minus 3, and so on. All right, so now this is easy. You just take all these guy out. All right, all these guy at most ON of them. So you have ON, and then you have the inside is ON plus ON minus 1 plus ON minus 2 plus dot 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 plus ON1. Okay, so just simply taking this, broken it into two parts. The first part is O1, 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 O1 is ON, ON minus ON, ON minus 1, ON minus 2, and so on, plus the ON at the back. Okay, so this is O of 2n. This one plus this is simply ON plus, now you see this n plus n minus 1 plus n minus 2 plus all the way until 1. So this is 1 plus 2 plus 3 until n. So this is n times n minus n. This is simply n plus 1 times the number of terms, which is n divided by 2. And this is simply O of that. All right, so ON is smaller than ON squared, so you just simply have ON squared. Okay, so this is the time. What about the space? Space, most of you say ON. So when I calculate this factorial 5, how much space I use? How much space I use? I needed to, in the iterative version, right? We are assuming iterative version. So I also use O1 only, right? So this is O1. And when I calculate factorial 4, I also use O1. Why? Because iterative, all right, iterative, you saw that I only needed to keep track of I and product, all right, iterative. So again, this is O1. And then all O1, okay. But Now you notice that I do put on hold all this addition. Okay. So actually I use O1 for the factorial, but actually I have a defer plus plus. So until here, I actually have defer 5 addition. Okay. Which is in general O and addition are on hold. Okay, waiting for me to do it. And that's why I do one addition, another addition. All right, I do this one plus this one, then another one, this one plus this one. So here it's 1 plus 1. Then this one is 0.5 plus 2. And this one is 1 over 6 plus 2.5 and so on. All right, so my footprint, now you see I have defer 5 and my footprint is ON. So the space is also ON. So the space is ON. All right, for this solution. Of course, you can actually do better. Okay. Why? You can actually do better, which is the here. Okay. If you do an iterative version of find E, I will not do that for you. You will have to do it yourself. Okay, I have a few more minutes. I wanted to go to question number 6. Are you okay? So most of you get it correct, but I needed to show explicitly why you are correct. Okay, give me a check and then we go to the last question. Okay. The last question is something which are kind of unusual. You are told that this guy is divisible, will take ON time and O1 space. Actually, if you write it out yourself, it looks something like this. Okay, question 6. If you write it out yourself, it looks like this. All right, it's divisible xi, return not x divided by I. If x is divisible by I, then you return true. Okay, otherwise it's false. By this simple statement, actually it doesn't need ON time. It just simply need O1 time. But you're told that it runs in ON time and O1 space. So even though we know how to do it in O1 time, but you assume that you don't know because the question give it to you in this manner, so you have to do it this manner. Now your job is to write its prime function and return true if it is a prime, otherwise false. Can I see some posting in your chat box? Then I can work on it. All right, question 6. Okay. Anyone? Okay. All right, some more. Okay, I haven't seen I've yet to see the more correct solution. No, some more. No. Any more? Okay, never mind. Okay, let me put it down my. All right. So okay, I will give this to you. All right. N equal to 1, usually we don't take it as prime number, so we return false. N equal to 2, it's always true. And 2 is considered as a prime number, so okay. Then it's divisible because all the even numbers except for 2, it's for sure prime. So this guy are not prime. Any number which is divisible by 2, it's not going to be prime. So you return false. Otherwise, now you get rid of those even number. So you can start from 3, right? You don't need to take care of 1 and 2 and all the odd number, you don't all the even number. So you start from 3, you increment by 2. All right. And another trick here is that if whenever you have a number that divisible by another number, that number is going to be less than the square root of it. All right, so we can stop at square root of that number plus 1, just 1 larger. Okay, so this range is good enough to complement whatever is up here, and starting from 3, stepping with 2, and so on. So when you do that, if it is divisible by the number I is divisible by n is divisible by the I, then you know it's not a prime, so you return false. After you finish everything, you still haven't returned, then you return true. Okay, so this is O of 1 time for sure. This is O of 1 time for sure. But this guy is told that it's On time, so it's On time. And this step, it's like taking On raised square root of n and half of it. So this is exactly this times this, which is exactly your this thing. Okay, this divided by 2. Oh, sorry, not this thing. So I better write it up. So this algorithm is actually so the time is O n raised to the power 0.5 divided by 2 times On. Okay, because of it is zero, and this is equal to O of n raised to the power 1.5. Okay, and what about the space? Space, this is a constant here. This one doesn't use much space, O1 space. And I is a variable. Range is so this is constant. This constant is stepping with 2. So everything is constant. So this is O1. Okay. And that's all. You okay? Question. This could be an interesting, question 7 will be interesting to write yourself and analyze it. Next week I'll do it for you, but not now. Okay, any question? Or if not, we pass 9:30 and it's time to finish. Yeah, exactly 9:30. Okay, if you're okay, give me a check and you can go. Okay, today is a long one. All right, the recording will be up by tomorrow. You can then check it out further. So I noticed that you guys have to practice more on the complexity. There will be quite a number of such questions in the past midterm. You can try on them out. Okay, if nothing, you can quit. Okay, bye-bye. What happens if n cannot be squared? Or it can round up. This is integer. And then we play safe by adding a 1. We're off by a little bit, it's okay. How did you get ON squared? Oh, this is simply, all right, so I start with 3, and then I stop here. So what is this? This is at most this number, right? And I always step by 2, so I divide by 2. That's how I get it. 孙思源. Is that okay? Okay. All right, it's simply here. That's why I do this. I start from 3. And I skip every alternate number. So I have 3, 5, 7, 9, 11, and so on. Okay. Bye-bye.